Physics Part 258. Satellites are widely used in telecommunication. Many communication satellites are placed in what is called geostationary orbit. That is, they are in equatorial orbits with exactly the same period of orbitation, with the same period of rotation as the Earth, and move at the same direction as Earth so that they are always above the same point on equator. Details of the orbit of such satellites are worked out in the example which follows. We've got an example for you. For a geostationary satellite, calculate the height above the Earth's surface, calculate the speed in orbit, calculate as the radius of the Earth is 6.3 into 10 power raised to 6 per meter, mass of the Earth is 5.9 into 10 power raised to 24 kilogram. At the period of satellite is 24 hours, which is equal to 8.64 into 10 power raised to blah blah per seconds. Using t square over r cubic, 4 pi square is equal to gm. We have r cubic 6.67 into 10 power raised to 11 into 5.98 10 power raised to 24 into 8.64 into 10 power raised to 4 whole square, 4 pi square, giving r cubic 7.54 into 10 power raised to 22 per meter. Taking the cube root, the radius r of the orbit is 4.23 10 power raised to 7. The distance above the Earth's surface is 4.23 into 10 power raised to 7. 6.4 into 10 power raised to 6 is equal to 3.59 into 10 power raised to 7 per meter. B. Since v is equal to 2 pi r over t, the speed is given by v is equal to 2 pi into 4.23 into 10 power raised to 7, 8.64 into 10 power raised to 4, 3000 centimeter per second. Now it's your turn. The radius of the moon's orbit is 3.84 into 10 power raised to 8 meter, and its period is 27.4 days. Use Kepler's law to calculate the period of the orbit of a satellite orbiting the Earth just above the Earth's surface. Communication satellites are considered further in our upcoming tutorial as well. Well, now we talk about weightlessness. Suppose that you are carrying out an experiment involving the use of Newton balance in a lift, where the lift is stationary, an object of the mass 10 kilograms suspended from the balance will give a weight reading of 10 grams per Newton. If the lift accelerates upwards with acceleration 0.1 g, the reading on the balance increases 11 gn. If the lift accelerates the downward with acceleration 0.1 gram, the apparent weight of the object declares to 9 gram per Newton. By an unfortunate accident, the lift cable were to break and there were no safety restraints. The lift would accelerate downwards with acceleration g. The reading on the Newton balance would be 0. If during the fall you were to drop the pencil with which you are recording the balance reading, it would not fall to the floor for the lift, but remain stationary with respect to you. Both you and the pencil are in the free fall. You are expecting weightlessness. The figure illustrates your predicament. It might be more correct to refer to this situation as apparent weightlessness.